Welcome to AI Paper Slop. We are jumping straight in today. The paper is Reinforcement Learning from Rich Feedback with Distributional DAgger from a team at USC, Rishab Agrawal, Jacob Fine-Ashley, and Priya Rashidinejad. And here is the immediate 30-second summary you need.
Yeah, let's get right to it.
So if you're training reasoning models, standard RLVR reinforcement learning from verifiable rewards is basically bottlenecked because it relies on a single bit of final answer feedback. It completely fails at token-level credit assignment.
Right.
Now, people have tried to fix this with self-distillation methods, like SDPO or OPSD, using rich feedback to create a teacher policy. But the paper proves their math is just fundamentally flawed.
Yeah, completely broken.
They use local gradients that miss early mistakes, and they rely on divergence metrics that can actually mathematically decrease your expected reward. So the solution they propose is DistIL distributional imitation learning. It uses a distributional variant of DAgger with a forward cross-entropy objective and sequence-level gradients. Yeah. It guarantees monotonic policy improvement, sublinear regret, and is just crushing baselines on science, coding, and hard math right now.
I mean, to really understand why DistIL is such a breakthrough, we first have to, examine the mathematical exactness of why all those previous methods just fall apart.
Right, exactly. And I guess we should move from that summary to the baseline problem. Like, why are we even talking about distillation in the first place?
Because RLVR has a massive bottleneck.
Yeah.
Standard RLVR, in reasoning models, you basically sample responses and give a terminal reward, right? Like correct or incorrect, 1 or 0.
Yep. And
that broadcasts a single scalar weight across every single token in the sequence.
Okay, let's unpack this for a second, because to me it's like grading a 10-page calculus proof with just a C- at the very bottom of the page.
Yeah, exactly.
The student, or in this case the LM, has literally no idea which specific line of math ruined the whole proof. It's just like, try again.
Right, and it's even worse because RLVR really struggles in unverifiable domains, where you can't just write a unit test or check an equation.
Oh, sure.
This is exactly why the whole field moved to rich feedback. Things like execution traces, expert corrections, error logs, we take all that and use it to condition a teacher policy.
And then distill that back into the student on policy self-distillation.
Exactly. So if rich feedback is the answer, the big question is, why aren't methods like SDPO and OPSD enough?
Because mathematically, they don't actually guarantee the model gets better.
Yeah.
Which is wild to think about.
It is. And this is the paper's first major takedown. Prior methods use these f-divergence objectives like reverse KL and SDPO or Jensen-Shannon and OPSD. The researchers proved that even if a teacher policy is strictly better than the student, the natural policy gradient step, the thing minimizing these divergences, can actually increase the probability of worse actions.
Okay, here's where it gets really interesting.
Yeah.
Because they have this specific three-armed bandit counterexample in the paper.
Yes, the three-armed bandit.
Let's say you have an excellent trajectory, right? Reward of 1. A mediocre trajectory with a reward of 0.5, and a bad one with 0. Reverse KL normalizes this really weird way.
It does.
Where it can actually boost the probability of that 0 reward bad trajectory, just because the student overweighted the mediocre one relative to the teacher.
What's fascinating here is that the math actively punishes the model in the wrong direction. But that's just the divergence flaw. There's a second major flaw. Local credit assignment.
Oh, right, the stop gradients.
Yeah, so SDPO uses a token-wise local gradient. It effectively applies a stop gradient on the autoregressive sampling process itself.
Which makes no sense for reasoning.
None. The paper does this two-step contextual MDP proof. It shows that local gradients get stuck at a suboptimal, like 1/3 expected reward.
Because they just completely ignore how the first token choice shapes the future states.
Exactly. Whereas a full sequence-level gradient achieves a 2/5 reward because it actually fixes those early mistakes.
So, okay, having proved that reverse KL and local gradients are just broken for this, we get to the actual fix. Enter DistIL.
Oh, right, DistIL, the architectural fix.
How does it actually work under the hood?
So it uses forward cross-entropy between the feedback conditioned teacher and the student. But, crucially, it's evaluated on states visited by the student.
So it's a distributional variant of DAgger.
Precisely.
And when you look at the gradient decomposition, they split it into a local imitation term and then this future-aware credit assignment term.
Yes.
So what does this all actually mean for the listener? It means it's basically a butterfly effect mechanic.
I think the bisect.
Yeah. I get bisect. If token number 5 causes a massive teacher-student disagreement way down at token number 50, DistIL actually propagates that error back to token 5. It holds the early tokens accountable.
That is exactly right. And because it's forward cross-entropy, it easily accommodates black box teachers.
Oh, like human experts or external APIs.
Right. You don't need the internal log probabilities of the teacher model. You just need samples from the teacher. That is huge for actual deployment.
Okay, so intuitively, this makes a ton of sense. But what does the math actually guarantee for the practitioner who's running these expensive training jobs?
The paper lays out 3 major theoretical proofs. First is monotonic improvement.
Which means it only goes up.
Right. Because DistIL uses forward cross-entropy, the update moves the student directly toward the teacher policy. It mathematically ensures your expected reward increases. You don't get that weird reverse KL collapse.
What's the second proof?
Sublinear regret. This bounds the gap between the teacher and the learned policy. It depends on a few things, like ratio-based and KL-based concentrability coefficient.
The C and C0 terms.
Exactly, plus the teacher variance. But the really interesting part is the recoverability parameter.
The mu-T. Yeah, that part is super important because it measures the cost of a fatal early mistake.
Exactly. And the third proof is pass at n DistIL optimizes a lower bound on the teacher-weighted log likelihood of success.
Let me just zero in on that pass it end proof for a second, because for the ML engineer listening, why does this matter practically?
Right. Why care about the lower bound?
Because optimizing this lower bound inherently pushes the model to generate diverse, correct solutions. It's not just memorizing one narrow path, which completely explains why it crushes the standard empirical benchmarks.
Yeah, the empirical runs are where you see the math just leap off the page. Does DistIL do what the equations promise? Yes.
Let's talk about the benchmarks. They had 3 big ones, right?
Yeah, first was Science the Sino-Evil benchmark. They ran it on Quen 3.8b and Ulmo 3.7b.
And DistIL is incredibly stable there.
Unbelievably stable. Meanwhile, SDPO literally collapses on the biology subset after just 100 steps. It just oscillates wildly.
That's the 3-armed bandit flaw happening in real time.
Exactly. And on physics, DistIL sees a massive 8.1 to 9.6 point gain over the next best baseline with only 5 hours of training.
Wow, 5 hours.
Yeah. Then they did coding, Live Code Bench, or LCB v6. This uses execution-based feedback like unit tests, and DistIL just dominates.
But my absolute favorite part, the third benchmark. The hard math problems, AME and HMMT.
Oh, this is the best part.
I love this detail so much. On these hard math problems, the base model has a literal 0 pass rate.
Can't solve anything.
Right. And because GRPO, which is everywhere right now, relies entirely on verifiable terminal rewards, you get 0 advantage signals.
If you never accidentally get it right, you never get a reward.
Exactly. It's completely blind and just fails to improve at all.
Sure.
But DistIL just uses the ground truth to bootstrap from 0.
If we connect this to the bigger picture, it highlights the absolute necessity of rich feedback distillation in domains where exploration is just too hard for standard RL.
Right. Standard RL just wanders in the dark.
Yeah,
Okay, but before we wrap up, we need to prove why DistIL worked in these runs. We have to look at the ablation studies.
Yeah, the ablations really unpack the why. They did 2 main ones.
First one was credit assignment, right?
Right. So they replaced the full sequence-level gradients with a local cross-entropy bus line.
So they broke the get bisect feature.
Yes, exactly. They forced it to act locally, and immediately variance spiked and performance dropped. It empirically proved their third proposition. Local gradients are just suboptimal.
Okay, and what was the second ablation?
The top K ablation. They looked at how many teacher tokens to actually distill. It turns out distilling the top 100 teacher tokens works the best.
Wait, really? You'd think matching the full distribution would be best, right? Like, give it all the data.
You would think that, but no.
Yeah.
The full distribution forces the model to learn low probability noise. It's just uninformative artifacts.
Oh, so it wastes capacity on garbage.
Exactly. And top 1 is just too noisy and weak. It's too narrow. So top 100 is the mathematical sweet spot. It captures the valid diversity without the noise.
So the ultimate takeaway for you listening, if you are training reasoning models, standard RLVR and local self-distillation aren't enough. You need future-aware credit assignment. And DistIL provides the mathematically sound blueprint to do it.
It really does. And, this raises an important question to think about.
Oh.
If DistIL allows us to propagate future credit back to early decisions using black box experts, what happens when we start chaining multiple specialized black box models together?
Like a committee.
Yeah, as a committee of teachers, say one for logic, one for computation. Could DistIL effectively learn to route reasoning across different expert modalities natively within its early token generation?
Oh, wow. That'd be completely wild. I'd love to see a paper on that next. Well, thank you all for tuning into AI Paper Slop. Remember to take these insights and apply them to your own ML pipelines. Catch you next time.